Okay, I will go back, class, to that board, the Jamboard that we used last meeting, wherein we are discussing about the response of a specific pulse forcing function. Okay, let me share the board again to you. Can you see?
Wala pa, miss.
Oh, sorry. Wait, why can't you see? Share. Oh, wait. What you see is, wait, class, it's as if it's starting a new weight class. It should display the same Jamboard. It's here, it is. Okay, can you see it? Can I just see a reaction if you see it?
Yes, miss.
Okay, thank you. For this particular example I gave you last meeting, let me go back to the original, the first 2 pages. Okay, I gave here a pulse forcing function of magnitude 10, okay? That is going to happen. So the disturbance is going to happen from 1 to 2 time units. So it could be 1 to 2 seconds. It could be 1 to 2 minutes or something like that. So the unit of the time depends on the unit that is given in the problem. Okay, so we're here. What we did is write first the forcing function in this form. So 10 u of t minus 1 minus u of t minus 2. And then our forcing function, we took its Laplace transform. So it is now like this. Then if we're going to write our corresponding response, y over s still not yet inverted, it would be something like this. After we have this substituted already our x of s to this particular transfer function. So your y of s would be something like this. And so that you could see that we'll be dealing with the same function of s when inverted, we factored out the constant 10 over pi, and these are the rational expressions resulting. So you can see that the denominator is the same for both, and that's the product of s and the quantity s plus 1 over tau. Okay, so our goal here is that we will just invert the expression 1 over s times s plus 1 over tau and correspondingly shift it later. So applying the second shifting property. Okay, so if we do that, it would look something like this. So the inverse Laplace of this particular rational expression in s would be something like this. And then since it is of magnitude 10 for the first expression here, and the argument of the exponential function is -1. For the second one, we have -2. So we split it into 2. So you have here, the t will be shifted in a manner written like this. So t minus 1, everything else is as is. And then this is just a fix. So you have the u of t minus 1. Okay, for the second one, we will change the shifting. It should be t minus 2. The rest is everything. And this one actually, class, is the continuation in this part. So you have u of t minus 2. And now, I think this is the part we ended. I simply use the rules of exponent in the second term in here. and distributed the expression u of t minus 1 to the 1, and this particular expression wherein we are using the rules of exponent. Excuse me, class, I need to take a call. Okay, sorry about that, class, ha. We have our, by the way, I'm not sure if Sir Barcimo has already informed you. We have our convention starting Wednesday until Friday. And PG and OC informed me that the bank transfer was not made, so they have to pay for us and they need our individual information. Anyways, I will just call Renda later when we're done. So I'm here. Where are we? So we're here. The first part that you have in this particular line of our solution is only representative of this. So we need the second part. I will just continue in this part in here, and I'll just write it next page. Actually, it would look like this also. It will be an expansion similar to this, but instead of writing, you have here, this is e raised to 1 over tau. In this case, this would be now e raised to 2 over tau. Because if you're going to apply the rules of exponent, here you will have negative t over tau, and you will have positive 2 over tau for the second e. So the second term, same as this one, only that will differ in this part here, okay? In the constant. Now, for us to simplify this properly and for me to be able to illustrate how you're going to write the interval form of this response equation, let's say, I'll go to the next page, we'll have a specific value for tau. Let's say your tau is 1 time unit, because we need it here to simplify. And anyway, the rest is good to go. So I will have the expanded form in now in this written here. So you have 10. Oh, sorry. U of t minus 1. So you have in the second term, you have now, can you please multiply e raised to 1 or e raised to 1 to 10? So your e raised to 1 is, if I'm not mistaken, is 2.7 times 10, that would be 27. Can you give me the specific value for this one? That way I can write this as one expression.
I'm already done with
27.1828, Miss.
So we'll have 27.183. Okay, round off ko na lang. So that would be for the 10 times this one. And this e raised to negative t over 1, that would be e raised to negative t. So I'll write it here as e raised to negative t. And you also have u of t minus 1 in here. This would be for this part, the expansion of this. For the second, you will have something like is it a minus? Let me check. So it's a minus here, so I should write here minus also. So minus 10, but this time you will have u of t minus 2. And just like what we did here, in here, instead of having e raised to 1 over tau, this would be now for the second term here, it would be e raised to 2, or that would be 2 over 1. And that should be multiplied to 10, and that should be multiplied to u of t minus 2. Now, this being a minus here, and this one is a minus, so I should write here a plus. So plus. So can you give me please the answer for e raised to 2? Because this one now would be e raised to 2 over 1. Then please multiply it by 10. So we'll have a specific answer here on the fourth term for our solution. Or you can place it on 73.891. Thank you. So you will have here, let me just minimize. I'll write it here below, 73.891. This is e raised to, in this case, that would still be e raised to negative t. So over tau, which is 1. This would be e raised to negative t, but this time it should be u, sorry. So this should be u of t minus 2. The next thing that you do, class, is since they are already grouped together, this is how you're going to write it. You group all the terms that have the same, there's a different shifting in the u. So this one is 1, this one is 1, and this 2 also. So I should have not expanded it since I'm going to write it anyway in the same manner. So you will have here a 10 minus 27.183 e raised to negative t. This should be multiplied to u of t minus 1. In the second part, if I will have a negative here, minus, so this should be t minus, 73.891 e raised to negative 1, and this should be multiplied to u of t minus 2. Okay. Now, when you write your response equation, this is your response equation now for this particular pulse forcing function. So this is your pulse forcing function. And its response equation now is like this. Now, the problem with this response equation class is it still contains the u of t expression. So when you're given a particular time in which you are to determine the response of your system, you cannot still multiply simply the time value here for the t because it's written like this. So there's a need for you to convert your response equation into the interval form of the response equation. What do I mean by the interval form of the response equation? So it's actually still using what you have learned in advanced math. You write your y of t in this expression. So you have y of t equal to, and it will be written like this, wherein you have corresponding values of the function for the indicated time interval here. The procedure is very simple. You copy the first magnitude that you see here, written on the first u of the expression. So the set of magnitude, I say the set because you have a set of terms here, will be this one, 10 minus 27.183 e raised to negative t. So I'll write it in here. 27.183 e raised to negative t. Okay, the second class, the second magnitude that you're going to write, second I say because it's the second magnitude we are to place here, will be now the corresponding, and use a different color, corresponding combined form of this only, and this. So you need to add if it's an addition here, but in this case, since it is subtraction, you're going to subtract. So if you do subtraction class, you notice that this 10 magnitude and this 10 magnitude will cancel each other, leaving us with negative 27.183 e raised to negative t minus minus, so that would be plus 73.891 e raised to negative t. So if you're going to subtract 27.183 to 73, what should be the answer? I need help here. Can you give me the difference between 73.891 and 27.183? Anyone? 46.783. Thank you. 46.783. So I'll write here 46.783. Now, what will be the time interval that you're going to write here? That would be the time interval that is indicated in your response equation. So you see this one, I'll use a different one. This one and this one, this will be the interval that you're going to write when you convert this response equation in the interval form. So here, you're going to write 1, and then you have 2, okay? And then this one, since you see class, there's nothing written after this. If there's another term that is written after here, the interval will be the shifting in the second term and that of the third term. So since nothing is written here, then it would be only this one now. So you're going to write in here t greater than 2. Or anything that is not included in the interval here after. So that should be the interval for this one. So by the way, this should be, I forgot to write the exponential function, e raised to negative t. So now with your response equation written in interval form, let's say, for example, you are asked for the response after 1.5, let's say minutes, if it's the minute unit that is used for time, you're going to use this response equation. If you're going to be asked what is the corresponding response after 5 minutes, then you're going to use this equation. So you have to convert your response equation in this form to this form. That way you can appropriately write the correct set of, shall I say, expression we're going to substitute your time. That's it. So this is how you determine the response of a pulse function using Laplace transformation. Do you have any question here? None? Okay, so it's clear to everybody. So this is how you're going to write the response equation for a pulse forcing function of magnitude 10 and on the interval of 1 to 2 units. Now we're going to share, go back to the slide that I was using so that will be guided accordingly. Okay, I think we're done with the pulse. So we now go to the sinusoidal input. So let me share it now. Stop sharing and then share a new one. Okay, so this is our sinusoidal input. So this is applied to forcing functions which are periodic in nature, or shall we say cyclic in form. So they can be approximated by this particular representation. So your x of t expression is represented by a sine omega t. So it's going to start at time equal to 0, just like the rest of the forcing functions that we have learned before. And a here, so if you're going to define a, that would be the amplitude of the disturbance, whatever that may be, amplitude of the temperature, amplitude of the level. It depends on what is the system that is given to you. And omega is the angular frequency in radian per second. So that is the usual unit for the radian frequency here. For the angular frequency, which is radian per second. Now, so our forcing function, since it's periodic, it's likened to that of the sine curve. So the period of our periodic forcing function is given by 2 pi over the omega, which is your angular or radian frequency. Now, if our forcing function is represented in this form, its Laplace is a omega over sine squared plus omega squared, using the formula for the Laplace of a sine function. So this is the x of s expression for our forcing function. By the way, class, when you measure the period of your forcing function, it should be the peak-to-peak distance between two adjacent peaks ang sundanay, ang tupaday nga peaks ang imo nga sine curve. So not the next peak, but the next adjacent peak to it. Or it could be the alternate crossing. So the alternate crossing of your sinusoidal curve. So you can also measure the period of this forcing function starting in this point here and ending in here. The time unit that you'll be able to measure is the same as this one. The time from this peak to this peak. That is also the same as your period. Okay, so that's for your sinusoidal forcing function. And it's Laplace transformation here. So let me have this projected. Okay, now if we have a particular sinusoidal input, so this is your sinusoidal input plotted here, the output, as you can see, is lower in peak. So it's lower in peak than that of your input. So this describes the phenomena of what we call attenuation in the signal. There is the decrease in the value of the amplitude of the signal. So your input will, as expected, be higher in amplitude than your output. So this is your output curve, the one that is shorter. And in terms of lagging, you could see that the peak of the input happens first. The peak of the output follows after it. So there has to be your input peak should occur first and then followed by your output peak. This is the lag in here. So that's the lag time that you're going to measure later on. The difference between the time of the first peak to that of the forcing function and the time of the first peak also of your response function as plotted. But it could be this one also, the same distance malang na sila. Okay, so this is your period which I mentioned a while ago, measured based on the alternate crossing of your curve, your sine curve. And this is your lag time, your delta t. So your output lags behind your input, and that particular lag is referred to as the phase lag. The angle is always less than 90 degrees, or as stipulated in your book, it's approaching 90-degree value asymptotically. Now, if you're going to annotate, if you're going to substitute this let me go back to the previous page. Okay, if you're going to substitute the x of s in here to the Laplace to the transfer function for a first order system, this is the transfer function for the first order, you substitute this one, the x of s in here, your corresponding y of s when inverted will yield the expression I gave you. So you cross multiply, you substitute this one in here, and then cross multiply it in here. The corresponding function of s expression inverted will give you the response equation on the next page. So this one. Now, this is actually the exact response for a sinusoidal input. This is the actual. But what we're after, class, most of the time, and books would even specify it, what is being required is the steady state solution, or the final response, or the part wherein the response is already sinusoidal in nature. And in that case, that would be applying the concept of the final value theorem, wherein you are to determine the value of the function as t approaches infinity. And as a result, and as a consequence of that, if you're going to substitute t approaching infinity, this e raised to negative infinity over tau will be 0. So at steady state, the new steady state value of your forcing function will simply have the periodic term. So this is the non-periodic part, and this is the periodic part, or the sinusoidal part. So we are only interested in this. So most of the time, class, we don't include this one unless the problem specifies that you are to include the non-periodic response term of your response equation for a sinusoidal forcing function. So if you are asked for the response equation of a sinusoidal forcing function, it will only include this one, the steady state solution, or the final value of the response, this one. So it will not include this one anymore, because mathematically anyhow, this will be 0. Now in here, you can see that you still have the amplitude of the temperature in the case of the thermometer, whatever that be, the amplitude of the disturbance. You have here the radiant frequency, or the angular frequency, and you have here the phi. This phi is what we call as the phase lag, and oftentimes its value is negative, because the value that you're going to get after performing this particular or going through this particular expression on the right side of the equation will always be negative, telling you that your output will always lag behind your input by a value which is approaching this 90-degree value. Now you could see here an expression which is 1 over the square root of tau squared omega squared plus 1. This is the amplitude ratio. We call this the amplitude ratio if you have read the section that I've assigned you to read. So this is the amplitude ratio for our forcing function. Or shall I say the amplitude ratio of the output that of the input to that of the input. This value class will always be less than 1. So if your answer for this value is greater than 1, there must be something wrong with what you're doing, because it's explained that, and even you can see here in the curve, that the amplitude of your output is lesser than the amplitude of your input. So this is your input amplitude measured from here to here, where that of your output is measured also from here to here, but this one is lesser than this. So as such, it's important that this amplitude ratio will always have, or should always have, a value of less than 1 in the case of the sinusoidal forcing function. Okay, so this is your response equation for your sinusoidal forcing function. Now, it's very important, class, that you understand how this particular forcing function response for your sinusoidal input came about. So it's anyway, it's written in your book on after how you have simplified the original response equation after you have performed method of partial fractions, given the identities that are written in the book. So there were two identities that were given in the book, that for the P sine theta, Q sine theta equal to 0, and that of R equal to the square root of P squared plus Q squared. Now that's something for you to have read already and understood how that came about. But this one is a product of that. If you're going to use those two identities on your original response after you have done inversion, amo ni siya ang resulta. And what we are interested in is just the second part of this term. Okay? Now, for the sinusoidal forcing function, all you have to do, class, is substitute also the time here, the time which is stated in the problem, and then also the phi, which you are to predetermine using this formula also. Now, the tau and the radiant frequency oftentimes is provided also in the problem, so you can solve for this. And there's also a sample problem in the book which you can use in determining or in how to apply the principles illustrated here on a specific problem. So there's one problem there which you should have read also. So I will not discuss that anymore because that was assigned to you as well. What is important is, by the way, Kauhanor did not discuss how to determine the lag time. So there's this lag time mentioned in the sample problem. So if you have read the sample problem, what's the formula of the lag time? How do you determine the lag time? The time in which the output peak lags behind the input as stipulated in the problem. What's the formula for the lag time? Thank you, Joanna. Very good. So your lag time is your phase angle, absolute value, that is your phase angle over 360 times the frequency in here, class. The F is not the radiant frequency, but rather the cyclical frequency. So cycles per minute. So the F here should have a unit of cycles per minute or cycles per second. If the problem gave you the radiant frequency, just convert it to cycle per unit time. That should be the F that you're going to substitute here. As for the phi, that's the phi value that you got also when you perform this particular, when you process rather this particular formula. So it's not, the lag time is not really stated in the book, but you will learn about its concept in the sample problem. So don't also forget about the lag time. The lag time, the phase lag, the attenuation of the signal, or the amplitude ratio, the radiant frequency, and also all those things that are stated in the, shall I say, in the form of a set of conclusion after Kauhanor already performed the derivation of this particular response equation. for your sinusoidal forcing function. Okay, one thing worth noting, by the way, is that the radian frequency of the input and the output would also be the same. So your input is A sine omega t. The omega there is the same omega that should be submitted on the output omega in the formula. Okay. Any questions regarding sinusoidal forcing function?
Low. Low.
Okay, so there's no question in here. Okay, let me just clear my drawings in here. So this is for, okay, there's one here. Ang phi miss angle. Yes, the phi is, now, by the way, class, the phi is degree. When you answer the angle here, it should be in degree. If you're asked for what is the phase lag, your answer should be in degree. However, when you substitute it in here, it should be converted to radian. This should already be in radian. Why? Why do you think should this be in radian now? So the phi, when asked as in the form of a question, what is the phase lag, should be in degrees. When you substitute here, it should be in radian. Why do you think it should be in radian? You're welcome, Aliana. Why should this be in radian? Because, correct. Kaya hindi kaya ka-add sang degree na unit, dire kay ini radian unit ni siya. This is radian per unit time times the time, that should be radian. So this should be in radian also. Okay? When you answer for the phase lag, it should be in degrees. When you substitute, that was a good question. When you substitute here on the lag time, this one should also be in degrees. You don't convert it in radian, knowing that this is also radian. No, this should be in degrees. Okay, absolute value that is. In here, convert it to radian. Okay, some more questions? Miss, my question. Paano miss i-calculate ang time period if frequency is not given, miss? Frequency. What you mean frequency, Joanna? The radian frequency?
I think
The radian frequency? What frequency? The F?
Oo, miss. If, for example, miss, hindi given ang frequency diri sa lag time, di ba, miss, ang F is equal to 1 over T? Paano na, miss, if ang T, miss, i-calculate kung hindi given ang frequency naman niya, miss?
This one, this is your period. Let me annotate. This one is your period, right? So this is your T. Kaya na may formula kita sa period, no? This is 2 pi over omega. So that answers your question already?
Yes, miss.
This T is also, this, by the way, class, this T, write ko na lang D. Your period is represented as T. That's 2 pi over omega. In terms of cyclical frequency, that's 1 over F. So if this is not given, you can still solve for the period using the omega. Okay, the omega value. Any questions? Oh my, it's 10:15. Any question here? No more? Let me clear my markings. No more? So all you have to do, class, is know what the values of the omega, the tau, the time, okay, and know the principles behind sinusoidal forcing function. So hindi pwede nga ang output mauna pa sa input, nagasunod lang na siya. Okay, when you solve problems, just like the rest of the problems that you will encounter later on, you need not derive, you need not start with the transfer function. Go straight to the response. And as I have said a while ago, the response is only this. Unless the problem specifies that you are to include the non-periodic response, because this is your non-periodic response. Okay, let me proceed. So these are the things that I have mentioned already. So same radian frequency for both the input and the output. The output amplitude to the ratio of the output to the input amplitude is always less than 1 because output value is lesser than input. And this demonstrate the attenuation in the signal, or shall we say the signal value in terms of its magnitude is decreased. So there is attenuation. And the output lags behind the input by an angle phi. Okay, it is clear that lag occurs for the sign of phi is always negative. Okay, now let me proceed. Now the last is used, this particular type of disturbance class is used as a, shall I say, a manner of simplifying a particular disturbance. Excuse me. If the disturbance only happened for a split of a second class, ideally you're still going to represent it as a pulse disturbance. If it's a type of disturbance which is not sustained, sudden and not sustained, even if it's just a small fraction of a second. However, class, just for simplifying the process of determining the response, you have this option to use this particular mathematical, shall I say, simplification. So it's used for example, an electrical noise spike in a thermocouple reading. So a very small change like that in a thermocouple reading. So it's a split second disturbance, and after that it's done. So we can use the impulse input, or the injection of a tracer dye to a particular, let's say, experiment that is being done. So this could also be approximated. So this is just an approximation. If you're going to ask me if the problem is giving a type of disturbance that is sudden but not sustained, you are still going to use the pulse representation. Okay? But if the disturbance happened for just a split of a second, you are suggested to use this particular manner of simplifying. Pero kung wala giglas na gahambal, ang problem kung ano siya nga types ng disturbance ang gamiton, pwede ged nga i-impulse nyo na lang para dasig. Pero kung ang problem gusto nyo nga ano gid siya mas accurate ang imo nga response, pulse gina siya dapat kay ini siya gini siya ginagamit nga pang represent sang forcing function para lang ni siya pang simplify sang proseso sang pulse. Kay kung mag-pulse ikaw kalawig sang aton nga obrahon nga procedure, pero kung mag-impulse ka lipot lang, so pang approximate lang siya. Ang tutuod gid nga representation gihapon sang disturbance is the pulse input type, or the pulse forcing function type of representation. Okay, it's very simple Laplace transform, because for this forcing function, you have, this is our forcing function, the direct delta function, and its Laplace transform is 1. So you will actually only invert y of t equal to 1 over tau s plus 1 over tau, which leads to this particular expression. So you have a 1 over tau in here. So your tau y of t is equal to this one without the 1 over tau inverted. So that would be e raised to negative t over tau. So you can see here the plot of the response of this type of approximation for the real pulse forcing function. So this is its plotting of the response. So at time equal to 0, there's an abrupt rise to 1.0 right away of the response for this type of forcing function. Then it will exponentially decrease as time approaches infinity. So as it approaches infinity, your response will be, of course, equal to 0, approaching 0. Okay? Again, let me emphasize that this representation of the forcing function is only for approximation purposes, for simplifying only. The real representation is still the pulse forcing function. Okay? Any question in this part here for the impulse input? There's none? Okay. So for tonight, I gave you, let me check, let me stop sharing. Let me check what's in the slide here. So this is now, by the way, the summary of all the responses, input and output for the 4 types of forcing function. The pulse was not included here. Did you ever wonder why the pulse was not included here in the summary? Why do you think the pulse was not included? Anybody who has an idea why nga ang impulse pang approximation lang ang ginsulat dire, ang pulse wala ginsulat? The real representation for a sudden and unsustained type of disturbance is actually the pulse. The impulse is just an approximation. Why do you think the pulse is not included here? Anyone who has an idea? Varies. What varies, Eugene? Very good. So Eugene is correct. So, hindi siya ma-derive ang response, ang pulse forcing function, kaya in the first place, nag-vary iya duration. It could be a series of pulses class. So, the example that I give you, by the way, is just one pulse. So, in the duration of 1 to 2 time units. What if you have a series of pulses? Like, you have a different magnitude from 1 to 2, then from 2 to 5, lain naman yung magnitude. So, that would be a series of pulses already. So it cannot be written into one derived response equation because, as what Eugene is saying, there's what varies are the magnitude and the duration. So hindi siya mabutang as one response equation. So kisa basta split second lang para hapos ang life, so pwede i-approximate using the impulse. So this would be your different response equation for the different types of inputs. The Kp here is the process gain. The K is, we know, is the steady state gain or simply the gain. Okay, for our first order system, whatever is the number that you see written on the top of the, actually in this case class, our transfer function should be still written in this form. Whatever is the constant you see in the numerator over tau over s plus 1. In this case, this is your gain. The entire constant in the numerator after, sorry, this should be, here go again, I forgot. Your denominator is written in this form, s plus a constant. So that is always the form of the transfer function of a first order system. In our book by Kauhanor, it's written like tau s plus 1. It's okay. Kaya ang tau pwede mo malamang pang divide both sa numerator kag sa denominator. But in terms of the form of the transfer function, it could be like this or this one. Okay? These are the summary of the forcing functions and their responses. Okay, by the way, in here, you have both the forcing function and the response plotted in one graph. The same thing in here for the ramp. This one is for the impulse, and this one is for the step response. Okay, so these are their different plotting. Nagsulit. Okay, and this would be the end. Now, actually, class, let me stop sharing. And I will stop